Hello, everybody. Let's start. We have Eric Allender from Rutgers. Eric had lots of works on complexity and meta-complexity, and today he will tell us about Kolmogorov complexity and statistical zero knowledge. Thanks, Eric.
Thanks a lot. So you see the title up there. I will explain those terms for anyone who needs them. This is joint work with Shuichi Hirahara and my PhD student, Harsha Tirumala. And for those of you who maybe think you don't care about Kolmogorov complexity or maybe statistical zero knowledge either, this is the reason you want to stick around to the end of the talk, because these results on the face of them have nothing to do with the question of whether or not NP is equal to NL. But Shuichi and I are actually convinced that the results we're presenting open up a promising line of attack to separate these complexity classes. And if it was just me saying that, I think you could just dismiss it because I've been wrong lots of times. But Shuichi has a pretty impressive record of coming up with surprising progress where it didn't seem so likely. So that's the motivation for you to stick around. Just so I know who I'm talking to, do I need to do a refresher on what Kolmogorov complexity is? How many people do not know what Kolmogorov complexity is? I don't want to waste your, okay, thank you. So Kolmogorov complexity is just a way to measure how much information is in a string. And the definition that has turned out to be more useful than any other is to say K of X is equal to the length of the shortest description D. Let me say K sub U, where U is some universal Turing machine, such that U on D outputs X. I'm lying a little bit. This is the definition for what's sometimes called plain complexity, but this capital K stands for something called prefix complexity. Fortunately for our main results, it doesn't matter which notion we use. So let's use capital K, and it's just a measure of how much a string can be compressed. And there's this annoying thing that if you change the universal Turing machine, you get a different number for how much information is in a string. But the good news is that Ku of X is equal to Ku prime of X plus or minus a constant. So you pick any two universal machines, they're basically going to agree on how much information is in a string. So this has been around since the 60s, large body of research on it. But one thing that's really annoying is that it's not computable. So why is a complexity theoretician interested in this non-computable measure? Good reason, or good question, because it's not clear that there's any reason why a self-respecting complexity theoretician should be interested. Nonetheless, for like 20 years, I've been banging my head on the wall, trying to figure out just what the connection is between Kolmogorov complexity and ordinary computational complexity. And what started 20 years ago to set this all off was the following strange result. We were looking at something called time-bounded Kolmogorov complexity, which is computable and has got connections to circuit complexity. But we showed that p-space is contained in the class of things polynomial time, Turing reducible to the random strings. What is R sub k? R sub k is the set of all x such that the length of x is greater than or equal, because k of x greater than or equal to the length of x. So it's not compressible at all. And if you just flip a bunch of coins at random with very high probability, you're going to get a random string, or at least something that's not compressible by very much. So this is a weird result, because p-space is a good familiar complexity class. We're reducing it to something that's not even computable. So how interesting is that? I mean, I could also say p-space is reducible to the halting problem, but that wouldn't be so surprising. But we couldn't squeeze anything bigger inside here. And we didn't know if that was just because we were too dumb, or if maybe there wasn't anything bigger. And well, that's where things stood for a while. Then there were some other results. BPP is in the class of things polynomial time truth table reducible to R sub k. These truth table reductions, also known as non-adaptive reductions. So here, given an input, you come up with a bunch of queries, and you find out which ones of those are random, and then you don't get to ask your oracle any more questions. Here, you can keep on asking questions after you get your answers. So, and what else showed? I'm going to run out of room, so let me put things up here. Non-deterministic exponential time is in NP relative to the random strings. And notice that this was the first time that we were actually showing that this oracle was good for something computable, because you know, we don't know that P is different from P space. We don't know that P is different from BP, but certainly NP is a lot weaker than next. So, you know, it's not a totally useless oracle. Well, still, this was a collection of weird results, because there wasn't any reason to think that these things really ought to be anything other than all computably enumerable sets. But there's a strange thing happened. Not very surprisingly, these inclusions hold no matter which universal Turing machine you use to define Kolmogorov complexity, because that's kind of the point of Kolmogorov complexity. It doesn't really matter which universal Turing machine you pick. But if you look at the things that are, let's say, non-adaptively reducible to the random strings, no matter which universal Turing machine you pick, turns out you get a subclass of p-space. Whoa! P-space is sandwiched between the things that are polynomial time, non-adaptively reducible, and adaptively reducible to this collection of, you know, the random strings. And in fact, there's a slight improvement that's I'm just going to put down here. This holds even if we're not just asking is the string random, but we're asking what is the actual complexity. And similarly, how do I want to draw this picture? I want to say that next, so NP to the RK is contained in NP to the K, and that's contained in exponential space. Okay. So, hooray, these things are actually complexity classes somewhere. You know, it contains p-space and it's in exponential space, if we're talking about this class, the class of things polytime reducible to the random strings. I drew this the wrong way. This was polynomial time, truth table, reducible to K. And here, I'm going to draw this way up here, P to the K, where that's there. So in fact, I was making a bunch of wild conjectures, maybe thinking that this wasn't just an inclusion, but maybe a really great characterization of BPP. Wouldn't that be nice? Or maybe we could get a characterization of next this way. Wouldn't that be nice? Well, Shuichi came along and blew all these hypotheses right out of the water. So what did Shuichi do? Being the clever person he is, he showed that non-deterministic exponential time is in RP non-adaptively reducible to the Kolmogorov-random strings. And of course, that's contained in there. And here's x to the NP. X to the NP is in, I knew I didn't draw this right. So polynomial time reducible to computing the Kolmogorov complexity function has got this huge complexity class in there, x to the NP, okay, bigger than non-deterministic exponential time. Maybe there are some other inclusions we want to present, but so basically my program of trying to characterize complexity classes in terms of efficient reducibility to the random strings lay in ruins. Certainly didn't look like we were going to get BPP or P space. I mean, we're talking about something way up high. Also, when I was noticing the lack of progress toward actually characterizing complexity classes, I said, maybe we're asking the wrong question. Maybe we want to talk about approximations to the Kolmogorov complexity function. If you're just changing the universal Turing machine, that's like a order 1 approximation, additive approximation. But we can talk about a promise problem, R tilde K, where the yes instances are the set of all x such that K of x, let's say, is greater than or equal to length x over 2, and the no instances are the set of all x such that K of x is less than length x over 2 minus some error term. Well, actually, Shuichi's results, his hardness results, carry over when the error term is as big as logarithmic. But then Mike Saks and Rahul Santhanam said, well, let's look at bigger approximation errors. So let's look at the approximation error. In fact, for the rest of this talk, the approximation error is going to be E of n is strictly more than logarithmic, and it's n to the little o of 1. So we're not getting the exact answer, but we're getting something that says, yeah, the complexity is really high, or no, it's really low. And they showed this amazing result that if we look at things that are randomly, non-adaptively, actually, I should do it this way. Let's look at this, draw it this way. Randomly, non-adaptively reducible to this promise problem. Well, then you get a subclass of AM. So what's kind of shocking about this is that with as much as a logarithmic additive term for the approximation, you get something that's harder than exponential time. But if you have just a little bit more error, more than logarithmic, then you're way down here, practically in NP. And they had another result talking about randomized reductions. And I'll remind you what randomized reductions are. And there they said that things that are randomized reducible to this promise class give you a subclass of statistical zero knowledge. And Shuichi and I looked at each other and said, we can do a little bit better. So let's show what the theorem is. I'm going to erase the definition of what the promise problem is. I'm ready to state the theorem. Let A be a decidable promise problem. Everybody know what promise problems are. You've got a set of yes instances, a set of no instances, and maybe some don't care instances. Okay. The following are equivalent. Number one, A is RP M reducible to this promise problem. The complexity, the Kolmogorov complexity is more than 1/2 or well under 1/2. Or A is BPP M reducible to R tilde K. So what are these randomized reductions? It's just like, it's an M reduction, just like CARP reductions. You take an input and you produce an output Y, except now it's a probabilistic routine that's doing it. And so here, with an RP reduction, if it's a yes instance, then with high probability, I'm going to get something with high Kolmogorov complexity. If it's a no instance, I'm guaranteed to get something with low Kolmogorov complexity. With a BPP reduction, given X, I produce an output, and with high probability for yes instances, it's high complexity. For no instances with high probability, it's no complexity. So it's this usual thing between one-sided and two-sided error. If you're familiar with RP and BPP, and I'm assuming that you all are, but if you're not, wave your hands. So, Mark, I'm surprised you don't know this, but
always use a reminder.
So RP is contained in NP. It's the set of all languages A, such that if X is in A, then the probability over randomly chosen Y that the pair XY is in our set that's checking, recognizing witnesses is greater than or equal to, let's say, 3/4. And if X is not in A, the probability over Y that Y is a witness for A is 0. So, with NP, you just are looking for a witness. For RP, if you're looking for a witness, just a random thing is going to be a witness for you. But we're still NP. Anytime you find a witness, that's a proof that it's in the language. And if it's not in the language, there is nothing that will cause you to accept. BPP, we don't know is contained in NP. And BPP is just with high probability, you get the right answer. So, if it's in the language, most things will tell you it's in the language. If it's not in the language, a random y is going to say, no, it's not. Okay, so it's the same notion applied to reducibility. And what's the final part of this? A is in NIZIC. Now, if you didn't know what RP and BPP are, there's not a chance that you know what NIZIC is. I'm just curious, how many of you do know what NIZIC is?
Everyone but Mark.
I read the abstract, so like non-interactive zero knowledge proof, right?
That's
That's
right.
the only thing I know is the acronym.
So zero knowledge proofs are this wonderful notion that's got lots of applications in cryptography, and it's just theoretically interesting. And I'm not going to take the time to define it to you, but go and study it later. SZK, I'm just going to define as the class of all promise problems such that B is polynomial time reducible to something called entropy difference. What's entropy difference? It's the set of pairs C and D, where C and D are circuits. The circuits are going to be representations of distributions. So let's say C is a distribution that takes random inputs, uniformly random inputs, and produces some outputs. And you're interested in, well, what kind of distribution is this? And the yes instances are going to be where the distribution given by C is roughly the same as the distribution given by D. They're pretty close. Whereas the no instances are the distributions are really, really very different from each other. Where I'm not going to define the notions of statistical difference, but it's a well-known measure of distribution. Either they're practically the same or they're way, way different from each other. This is the promise problem that characterizes this fundamental notion called statistical zero knowledge. But what's NIZIC? Well, this is a notion of interactive proofs and what somebody can learn. And there's a non-interactive version where basically the prover and the verifier are looking at some shared randomness. The prover sends a message to the verifier, and there's no more communication. The verifier just has to make use of that. But if that's too, it's actually a complicated notion to define exactly, what do we mean by zero knowledge? So let's say that non-interactive statistical zero knowledge is the set of all promise problems B such that B is polynomial time reducible to something called entropy approximation. These are not my initials. I mean, they are, but it stands for entropy approximation. And what is that? The input is a pair, a circuit, just like this circuit, and a number. And the yes instances are that the entropy of the distribution given by that circuit is greater than or equal to k plus 1. And the no instances are saying that the entropy of the distribution is less than or equal to k minus 1. And everything in between is a don't care. Okay. Now these look like kind of similar problems, and in fact, they are. So what's known is that, let's draw a picture like this. Here's NIZIC. Here's co-NIZIC. Not known to be closed under complementation. Here's SZK. This class is AC0 reducible to this class. In fact, it's just by taking an instance of this problem, you can come up with a list of queries here, and if any of them is in this complete problem, then that decides your problem here. So that's the point. If there's anything hard in this class, then there's something hard in this class. So it's sort of like P to the NP and NP. You know, they're really closely related. And why do we think that any of these things should be hard? Well, cryptographers are really hoping that these things are hard to compute, in fact, hard on average, because a lot of their favorite candidates are based on the hardness of things there. Okay, so back to the main theorem. This is a really weird characterization of this complexity class that's really largely motivated by cryptography. You know, when they were defining this, there's no way that they would have defined the class this way. Reduction to this undecidable question about Kolmogorov complexity. No, but in fact, it's an exact characterization. Okay, so I'm sweeping a few details under the rug, not very many. What's everybody's favorite example of a randomized reduction? It's this result by Valiant and Vazirani that says that satisfiability reduces to unique satisfiability. Well, for that reduction, the threshold, you know, it says if it's satisfiable, then this randomized reduction is going to give you something in unique sat with probability, you know, 1 over, I don't know, 4n squared. That's pretty low. And you might think, well, you know, we're talking about probabilistic computation. You just fiddle with it and you can make the error probability go, you know, the error probability go to small. Here, the error probability is way more than 1/2. In fact, with randomized reductions, you know, there's a nice paper by Chang and Rohani and somebody else that says, you know, you have to pick different thresholds for different settings to see what's useful. Here, the threshold we're going to say is that you get the right answer with probability 1 minus n to the omega of 1. So the error probability is quite small, you know, less than 1 over n to the k for any case. Okay, so this is the main theorem, and I can talk about the proof, but I promised you something about NL and NP, and this isn't going to get us there. So is Zev here? Zev Dvir and co-authors looked at a different problem or different complexity class, which was a log space version of statistical zero knowledge. And similarly, you can come up with log space versions of Nizhik and co-Nizhik. Now, why did he do that? Well, because you get a complete problem here. I guess I erased what entropy distribution is, but the thing that's sort of trivial to do is to say, if you just define things right, and where you could get complete problems where the distributions are represented by branching programs, because branching programs are the non-uniform model for log space. But using these wonderful results of Ishai and Kushilevitz and Applebaum. In fact, we can look at ED where the entropy distributions, the distributions are represented by NC0 circuits. In other words, the circuit that represents the distribution has the property that each output bit depends on at most 4 input bits. So that's kind of neat. And similarly, Nizic L is the class of things reducible to entropy approximation, where these circuits are represented by, the distributions are represented by NC0 circuits. Now, Nizic L was something that really hadn't been studied until co-authors and I looked at it. And the reason that we did that, because that we were interested in the minimum circuit size problem, and we couldn't prove anything about the minimum circuit size problem, but there is a problem called MKTP, which is about a time-bounded version of Kolmogorov complexity. And we could show that it was hard for co-Nizic L under projections. Now, you probably don't know what projections are. A projection is a reduction that's computed by a circuit that doesn't have any gates. It means that each input is just connected to some wires, maybe wires connected to NOT gates, that project things into the output. So you've got like a template of bits, ones and zeros, some things that don't depend on the input at all. And then here's a particular input bit, and maybe it just gets fed into that spot, and maybe it gets negated and gets fed into that spot. And each bit is kind of shoved into some location in this template. So MKTP is, like I say, a version of time-bounded Kolmogorov complexity. So the yes instances are the things where we can find a short description. So that's the, MKTP is in NP. So the yes instances correspond to the low entropy distribution things here. And so Nizic L, via a very similar argument, we can show reduces to this promise problem via non-uniform projections. In fact, we get a characterization. Those things are equivalent. Similarly, we can say these things are equivalent. A is let's say log space, randomized log space M reducible to R tilde K, or A is randomized AC0 reducible to R tilde K, or A is randomized NC0 reducible to R tilde K, or A is in Nizic L. There's something weird going on here. I should have said this is under log space reductions. Nizic L is class of things log space reducible to entropy approximation. But I could have just as easily said AC0 or NC0 or projection reducible to this. And that's the usual thing that happens. SAT is complete for NP, under polytime reductions, or under log space reductions, or under AC0 reductions, or NC0 reductions, or projections. It usually just doesn't make any difference. Here we're looking at the same problem, and you get the same class for all of these really weak reductions, but you look at a little bit more powerful reductions and you get seemingly a bigger class. Well, one explanation for this might be that these are actually the same class. We just don't know how to prove it yet. In fact, I would kind of guess that that might be true. But let's ignore that possibility for now. Let's just look at these characterizations. What happens? Okay, MKTP is in NP. It's hard for Koenigsegg L. So what happens if MKTP is in Koenigsegg L? I'll tell you what happens. You get that there is these are non-uniform projections. There's a non-uniform projection such that, and let's give it a name, projection F, such that if K of X, well, let's say if KT of X is less than, length X over 2 minus something, but let's just say, length X over 4. Well, if KT of X is small, certainly that implies K of X is also small. And this reduction is mapping that low complexity string to a high complexity output. So you feed zeros in. If X is all zeros, that's low complexity. You get a high complexity string here as output. And simultaneously, if KT of X is greater than length X, 3, let's just say length X over 2. Or heck, why not 3/4 length X, whatever. Just pick a random string. You're going to get something with not only high KT complexity, but high K complexity. And that implies that the Kolmogorov complexity of F of X is less than length F of X over 2 minus this error term, something bigger than log length of F of X. So in other words, you feed basically no information in, and you get high information coming out, but you feed high information in, and you get low information coming out. You pour water in, you get milk. You pour milk in, you get water. And this is happening with a projection. I mean, the thing that makes it hard to talk about showing that something is not complete for a complexity class frequently is because we just don't understand what's going on with computation. There's this polynomial time reduction stuff that's happening with the reduction. But here we're talking about a projection, which is like just plumbing. There's nothing really happening. Well, the other thing that makes it hard is that we don't understand the thing that we're reducing it to, you know, satisfiability or QBF or, you know, whatever complexity class we're talking about. But here we're talking about an object from computability theory, you know, so information theory techniques should one, you know, we think it's plausible anyway, that basically information theory techniques ought to be able to show that this just can't happen. And if you show that that can't happen, then we know that ATP is not in NIZC L. And NIZC L contains, you know, here's log space, which is contained in NL, which is contained in a complexity class called DAT, which is everything that you can do with the determinant, a subclass of P. And this is in NIZC L. So if you show that this problem in NP can't be in there, well, then you've separated NP from NL. Furthermore, we can actually show that you can't even reduce the parity function via a projection to this if the gap is bigger than we're talking about here. So, you know, smart people, try it. You know, there's all kinds of non-relativizing techniques that are embedded here. You know, in particular, these technology, you know, these techniques of cryptography and NC0 that allow us to reduce the question: are there one-way functions in these pretty big complexity classes? That happens if and only if there are one-way functions in NC0. So, you know, we're building on those techniques, and, you know, they just haven't been necessarily applied or looked at here. So, so that's the connection why I think some people need to spend some time trying to see if there's anything to this approach. So how are these results proved? I've got a little bit of time to talk about it. Question?
So what is KT? How is it exactly defined here?
So there are a lot of different ways to define time-bounded Kolmogorov complexity. And
here it's a specific function.
pardon?
Here it's a specific function of x. There is no t parameter.
That's right. So a little history. The first way that you try to define time-bounded Kolmogorov complexity is to say KT of x is the minimum length of a description such that U given D equals x in time t. This is actually a useful definition a lot of times, but there are some things that are just bad about this. And one thing that's bad about it is you change the universal machine, you get something that's quite different. You know, universal machines just don't agree very well. And the way you usually fudge that is, well, you know, you change the time bound and we don't, you know. But it really bothered Leonid Levin. And so he defined something called K little t of x, which is the minimum length of the description plus log of the running time, such that U of D equals x in time t. So in that paper 20 years ago, when we were looking at, you know, I had this funny result about p-space reducing to the Kolmogorov-random strings, we observed that this is roughly the same thing as circuit size of x relative to exponential time. What does this mean? When we're talking about Kolmogorov complexity, x is just a string. But some strings are the truth tables of functions. I mean, any string that's I've got length 2 to the n is the bit string representing a truth table on an n-ary Boolean function. And every Boolean function has got a minimum size circuit. And there's pretty clearly a connection between circuit size and Kolmogorov complexity. You've got a great big circuit, a great big truth table. If it's got a small circuit, that's like a short description of the truth table. And if you change the circuit model to allow oracle gates, which is a weird thing to do, then that's what Levin's KT measure is about. Actually, Levin had a lot of other good reasons for looking at this measure. It's got a lot of other nice properties, but it doesn't give you the most natural connection to circuit complexity. And so what we did was change little t to capital T and said, let's just add the description length with the runtime instead of the log of the runtime. Well, you have to make a few extra changes, like instead of giving us the entire string, let's just say I want the ith bit, give me the ith bit. And you can do this, and that gets you something that's roughly the same thing as circuit size. So we were interested in the minimum circuit size problem, which kind of had something to do with Kolmogorov complexity. This makes it precise. And that's this. That's what this measure is.
What exactly did you?
Pardon?
What exactly was the input to you?
So the input is not only the description, but a number I.
Okay, so it's both the description
And I'm asking the machine to tell me what the ith bit of x is.
and
You know, there's some other stuff like is I out of range, you know, is it longer than the length of x? But basically it's this. And it's not too hard to show that this is roughly the same thing as circuit size. And a number of theorems about the minimum circuit size problem have been proved by first proving the theorem for this KT notion, and then frequently we can show it also holds for MKTP or for MCSP. Sometimes we can't do that yet.
R tilde k itself is not computable.
R tilde k is not computable. There's no way.
Somehow here you just use.
Oh, no, okay. That's right. If it were computable, we would have a non-computable thing in this complexity class. Can't happen. So computable things. But what do I mean by computable? Means that the yes instances, there's decidable, and the no instances, that's a decidable set.
Somehow the theorem is there is this undecidable class, and if I take any decidable subset, with no
If you take
restrictions,
any decidable problem at all, a decidable yes set of yes instances and a decidable set of no instances, if that is reducible to the random strings efficiently, then it's actually in this little complexity class. And vice versa. The entropy approximation problem, which I guess I erased, the entropy approximation problem in particular is decidable.
So a decidable promise, do you mean that if the input is invalid, you're allowed to not terminate, or?
Yeah, I don't care. In other words, what do I mean by a decidable problem? A promise problem is a pair yes and no. Right? I want this to be a decidable set. And I want this to be a decidable set. And they have to be disjoint because you can't have.
So why not, why kind of, I don't know, Ackermann function,
Yeah,
Kolmogorov complexity?
Absolutely.
Why isn't it not a counterexample here?
Because it's not reducible to,
But it's reducible to RK tilde or not?
no, it's not. It's not randomly reducible to R tilde K.
So R tilde, it's a restriction of R tilde K. So basically I throw out from R tilde K anything that's not verifiable by trying all problems.
No. The no instance, the yes instances of R tilde K are things with high Kolmogorov complexity. No subset of this, no infinite subset of this is decidable. There is not even a way to enumerate infinitely many things with high Kolmogorov complexity. If you put a time bound on it, okay.
Okay, so
I've gotten the high sign, I've got 5 minutes. Very briefly, how is any of this proved? For things that are in, or that, basically, we'll just look at the entropy approximation problem. How do we reduce entropy approximation to things with high Kolmogorov complexity? We just take random samples. So let's say we've got this circuit C. I want to know, is it got entropy, high entropy or low entropy? What do? I take a bunch of copies of it. And I feed random inputs into all of them, independent random inputs. And if it's high entropy, you can show this is going to have high Kolmogorov complexity. If it's low entropy, it's not. And you can do that. It's actually a lot easier to do that than to do it with time-bounded Kolmogorov complexity, which was the initial theorem we had. How about the other way? Let's say you're reducible to the problem, R tilde K. You've got this reduction. Well, what is the reduction doing? It's taking input X and some random bits and coming up with a query. A bunch of queries because, well, actually just one query because it's an M reduction. Notice that this is basically taking some random bits and producing some output. So you can view that as the representation of a distribution. X here is just hardwired in. And you can show that if your distribution, if your reduction is really producing high entropy, high Kolmogorov complexity things with high probability, it's got to have high entropy. And if it's producing low Kolmogorov complexity things with high probability, it's got to be low entropy. So you reduce it to entropy approximation, just because of the way the randomized reduction is working. So that's the brief insight. I think we're going to be kicked out in a few minutes. But again, the reason to care about this is I honestly think that this is certainly something that hasn't been tried, except recently we've been trying, we haven't been able to do it. But I think it's plausible that you can separate NL and NP this way, just by basically information theoretic arguments. And to be really ambitious, thinking that since for most problems of interest, the things that are AC0 reducible to the problem correspond to the things that are polynomial time reducible to the problem, maybe these classes are really equal, which would mean, among other things, that we'd not only be separating NL from NP, but we'd be separating P from NP. But I'd be happy just separating NL from NP, frankly. You know, I didn't talk about characterizing SZK itself, but since SZK reduces to Nizic, you can just combine these notions, you get a characterization with a different notion of reducibility for SZK and for SZKL. So the takeaway is we've got radically different novel ways to view these well-studied complexity classes of statistical zero knowledge. And finally, after 20 years, for the first time, we've got a characterization of a complexity class in terms of Kolmogorov complexity. And so just in time for my retirement. So I think I'm done and we'll be kicked out, but I'm happy to talk to people out there someplace.
So everyone here